In the last video, we saw that if I try to define measure in this way, I start with a set S, then I define measure over the entire power set, that is I define measure for all subsets of S, a non-negative real number with this property, then I get stuck. It does not play well with some further natural conditions that we would like to impose on mu. So people started to think about that, what to do. There were three different approaches by which people could tackle this problem. Now, one of the approaches, the approach that has given birth to measure theory, said that do not work with entire power set of S, instead work with only a sub-collection of subsets of S. That is, say that there are certain subsets of S for which mu is not defined. Now, these subsets we shall call, they are not measurable because I cannot measure them. And the other subsets, they will be called measurable. So some are not measurable and some are measurable. So the next question is, which subsets should be measurable? For this, we first look at the specific application area, namely probability as a measure. So in this case, we have S, and naturally we would like to say that the total probability of the entire set is equal to 1. So first of all, S must be measurable. So S is one set that should be measurable, otherwise we cannot even say that the probability of the total set is 1. Well, now suppose some set A is measurable, so you can talk about its probability. So probability that A happens. Now, would it be very meaningful if I say that probability of A is meaningful, but probability of A complement does not make any sense? Which is weird, because if probability of something is say 0.3, probability of its complement should be 0.7. If 30% chance it happens, then 70% chance it does not happen. So if A is measurable, then definitely I want A complement to be measurable. Otherwise, it will be a very meaningless situation. Then again, when I define measure, I had this condition, namely if A1 ... AN, these things are measurable. Well, I just said it's possibly infinite, A2 ... Then, if these things are measurable, I said I will be working with their unions. So, this union should better also be measurable. So if these things are measurable, then these things should also be measurable. So I can say that the entire set must be there. I can see if something is there, its complement must be measurable, and countable union should also be measurable. Now there is a law called De Morgan's law, which expresses intersection in terms of union and complement. So when I allow union, countable union, and when I allow complement, naturally countable intersection also gets included. So if A1, A2, etc. are measurable, then their intersection is also measurable. I do not need to put that as a separate condition. It automatically gets included. So I have a collection of objects, collection of subsets of S that satisfies these conditions. That will qualify to be a domain of our measure. And this is called a sigma algebra, or sometimes also called a sigma field. The precise definition is, it's a collection script F of subsets of S such that the entire set is in script F, and this collection is closed under complementation, union, and hence automatically intersection. That is, if any set is there, its complement is there. If a countable collection is there, I should say countable union, and this is also countable intersection, not necessarily arbitrary union and arbitrary intersection. If you include this, then automatically this is included. If you include that, then automatically this is included, thanks to complementation and De Morgan's law. So now our second attempt at defining measure will be, we start with a set S, And then we start by fixing some suitable sigma algebra over S, that is a sigma algebra consisting of certain subsets of S satisfying those properties. And here we are careful to avoid all those complicated pesky sets like the construction that we saw in the last video, that set M. We do not want to put them in our script F. Then we define mu only for those subsets, non-negative real number, with the usual condition. Now, this thing was motivated by considering probability as an application area. There is a problem if I try to do something else. Suppose I am thinking of length, not probability, and I am working with R, the entire real line R. So the role of S is being played by R. So I take some particular subset, suppose this subset 0, 1. And I want to talk about its length. Well, I can do that. So its length is 1. Now I said whenever I have a set, I must have measure for its complement also. So complement of that set is this. What it should be its length? Well, its length should be infinite. Now I have not allowed infinity here. So just to accommodate these cases, that is unbounded measures, where things can be very large, I will also need to include infinity. Now that might be a bit shocking. What is meant by infinity? This is not a real number. So I would rather like to write it as union, a special symbol called infinity. So infinity is really not a real number. It's just a symbol denoting such situations. Then there is a little problem, because now mu can also take the special value infinity. Then what do I mean by adding? Well, that we will define or extend addition in the obvious way. So if A and B are both in real numbers, in that case it is usual. If you are trying to add infinity, then you get infinity. Now this addition you can easily check is still associative. Of course, this is a new operation. It is still associative. It is commutative, but unfortunately it ceases to be invertible. That is, if I have A plus B equal to A plus C, from this I cannot immediately conclude B equal to C. That is not true anymore when this is infinity. Because infinity plus anything is infinity, so from this I cannot immediately say that B is equal to C. So just like division by 0 is not defined, so subtraction of infinity is also not defined. But anyway, we are not going to use that. So this addition, this new addition is less powerful than our usual addition, but that is enough for us. So now finally we have arrived at our definition of measure as it is used in measure theory.